available. One is junction field effect transistor. Those are mainly used for power application. Metal oxide field effect transistor. Those are mainly used for logic and memory application for most of the digital ICs. So let's look at the functional block diagram of a MOSFET transistor. A MOSFET transistor is named, as I said, from the material organization: metal, oxide, semiconductor. In the total structure, it has five different material components. The first one, the top one, is the gate. The second one is the insulating oxide made of silicon dioxide, which is providing an electrical separation between gate and the body of the terminal. The body of the bulk of the silicon contains a source region, a drain region, and rest of it is called body or bulk. So in terms of material, we know that source and drain will be of same type. It will be either N plus or P plus. What that plus sign means? Plus sign means that it is heavily doped. That if it is N plus means it has a heavy concentration of donor atom, so that it has lots of free electron. If it says P plus, that means it is heavily doped with acceptor atom, so that it has many more whole atoms compared to electron. So on the other hand, body terminal, body area will be regularly doped. If source and drain are N type, body will be P type. If it is N plus, it is simple P. If source and drain are P type, P plus and P plus, body will be N type. So we have to remember, body of the transistor will be always opposite to the source and the drain in terms of doping. And source and the drain will be always heavily doped. Extra concentration of free electron or extra concentration of hole. So during the operation or running of the transistor, gate terminal, source terminal, and the drain terminal, these three regions will actively take part in current conduction. So on the other hand, the body region and the terminal that will come out of the body region will be kind of a passive terminal. It will not directly take part in the current conduction on-off operation, but it will provide kind of a basis, a ground reference point for the rest of the transistor, and also it will provide kind of a physical housing or holding for source and the drain region. So as I said, there will be three active terminals from any MOSFET transistor: source, gate, and drain. This particular version is called NMOS transistor, N-type N-channel MOSFET. In N-channel MOSFET, source and drain are of N-type, body will be P-type. P-channel MOSFET or P-type MOSFET, source and drain will be P-type, body will be N-type. Why this one is called N-channel MOSFET? Now let's go back to PN junction. Here is N-type source is touching P-type body. So along the periphery of the source and body, this contact, PN junction will be formed. When PN junction is formed, a barrier potential will be formed. Due to that barrier, current cannot conduct from source to body in any direction. Same thing, drain, N-type will form P-type junction here. Here source and drain P-type, body N-type, they will form PN junction around the periphery. Those PN junction will have potential, barrier potential, so they will not be able to force current. Now, when the transistor is on, that means I have to establish an electrical connection from source to drain. Easiest way to establish that connection is to connect source with the drain with the same type channel. If it is N-type source, N-type drain, if I can establish an N-type layer here, that means more electron, PN junction from that region will disappear, because for a PN junction to form, you need the presence of N-type touching a p-type. But if somehow if I can accumulate lots of negative particle here, electron here, that region will become n-type under the surface of the gate. So from source to drain, I will have a layer of n-type region to connect electrically source with the drain. Similarly, in this p-channel MOSFET, I have p-type source and p-type body. In between, I have two p-n junctions sitting, electrically isolating them. To connect them, if I can produce a layer of positive particle hole, that means a p-type channel, then I can establish a connection from source to drain. Then current will flow from source to drain. So, for NMOS transistor, to turn it on, I have to establish an n-type channel, electrical channel from source to drain. That's why it is called n-channel MOSFET. For p-type MOSFET transistor, to establish an electrical connection from source to drain, that means to turn on the transistor, I have to form a p-type channel from source to drain. That's why it is called p-channel MOSFET. In short, it is NMOS, it is PMOS. So now the question is, how do we form the channel? We will explain it, but from the body, this bulk of the silicon, there will be another terminal, body terminal, which will not take part in regular operation, current conduction and on-off operation of the transistor, but it will provide a bias or reference plane for rest of the voltage to be measured and applied. So it has to be connected, the body terminal has to be connected permanently with a reference voltage. In any digital logic circuit, there are two reference voltage. One is VDD, the supply, the other one is ground or zero voltage. And we already explained the symbol. This indicates that gate is isolated, insulated from the rest of the body by the presence of this gap. Same in here, but this bubble here with PMOS indicates that to turn on this PMOS transistor, I have to apply a negative voltage. Yes?
Can you explain the reference voltage that you told?
Okay. So, whenever you are measuring any voltage, you have to measure that voltage with respect to a reference. In any electrical circuit, you have two references, supply or the ground. So, sometime you measure the voltage, whether it is above or below the supply reference, or it is above or below the ground. So you have to have a reference point to actually measure any voltage. So there can be two possible reference, one is supply or can be ground.
I have another question. Most of the time, now I remember because it's way 1 year back. So most of the reference voltage is ground voltage, right?
No. In case of logic circuit, half of the reference voltage is VDD for all PMOS, half of the reference voltage is ground for all NMOS.
NMOS, okay.
Yeah. So now that it will be clear, now the question is, when we say we have to apply a positive voltage to turn this transistor on, what do you mean by turn this transistor on? We have to establish a channel to provide an uninterrupted electrical connection from source to drain so that it can carry current from source to drain. If I connect it to the battery, current will flow as long as there is a channel connecting, N-type channel connecting source to drain. So, presence of the channel connecting source to drain means the transistor is in on state. If whatever excitation or voltage you are using to form the channel, if that voltage is removed, the channel will disappear and the transistor will be in open or off state. Now, from the definition itself, now you know why this one needs a positive voltage. That positive on voltage, earlier we mentioned, gate is the control terminal which will turn on and off this transistor. That means from the gate terminal, we have to apply the electrical field to form the channel. Now, to form the channel between N-type source and N-type drain, we have to form an N-type layer. Now, on the gate, What type of electrical field we have to apply? Positive electrical field. Because positive electrical field will attract electron from source, from drain, and there are some minority electron lying around here and there, right? So if I apply a positive gate voltage in an NMOS terminal, gate terminal, this gate layer will become positively ionized. That positive charge will attract electron out of source, electron out of drain, and all the minority electron lying around, roaming around, they will be all attracted to the surface area because it is attracted by this positive pole. So, as we increase the strength of this positive electrical field or positive voltage, more and more electrons will gather under the surface of the gate, and when it reaches a critical mass, we will find a continuous channel from source to drain. At that point, we can consider that there is a channel established, the transistor is on. So, because in the N-type channel, we have to gather a layer of negative electron, we have to attract it with using positive voltage. That's why we have to apply positive voltage, positive electrical field at the gate of the NMOS transistor to turn it on. PMOS is opposite. This slide is very important, understanding the basic operation. PMOS is opposite. When we apply a negative voltage at the gate terminal, a ground potential, this gate plate will become negatively ionized. It will exercise attractive force on the holes, positive particle, from the source drain and the minority holes lying in the N-type part. All of them will be gathered here. When this negative voltage reaches certain magnitude, enough hole will be gathered to form a channel, producing a continuous connection from source to drain, so the PMOS transistor will be on above and beyond certain negative voltage. Below that, no channel will be formed. So, in terms of MOSFET functionality, as I mentioned, its main function is to work as a switch. There are two types of NMOS transistor, PMOS transistor, NMOS and PMOS. Now let us see, based on the previous slide's explanation, for which voltage condition, how these switching characteristics will be demonstrated. For NMOS transistor, if we apply a zero voltage or negative voltage at the gate, no channel will be formed, so it will be like an open or off switch. If we apply a high voltage or VDD at the gate, logic 1 means high voltage supply, right? If the gate logic is 1, that is we are applying a high voltage at the gate, then a channel will be formed, it will be on state. In case of PMOS, it is opposite. If a negative or ground voltage is applied, a channel is established and PMOS transistor switch is on or closed switch. If the gate voltage is applied, it is off switch or open switch. So this is showing the NMOS switching behavior. Now let us look at step-by-step operation, how the channel is formed. Now we establish the fact that for an NMOS transistor, to turn it on, we have to apply a positive gate voltage at the gate terminal. Now, the question is, if we apply any voltage above 0, that is a positive voltage. But will the transistor become on right after you apply a certain voltage above 0? No. Then it will go through several steps before a channel, reasonable channel is formed. So today we are going to explain how a channel is formed, how a transistor is turned on and off for a long channel device. This is a definition I want to introduce you at this point. What is a long channel device? It's just a classification of devices. Device now can be divided into two groups, long channel device and short channel device. There is no mark that up to this length it will call long channel and below that length it is called short channel. It's a relative term. First, let us look at the cross section of an NMOS transistor. Everything we explain for NMOS transistor will be exactly similar for PMOS. Only thing, supply will become ground, ground will become supply in terms of what we apply at the gate. So there is a dimension, the most important dimension, as you know, the length of the channel, which is the technology size. The width of the transistor, thickness of the gate, thickness of the silicon dioxide, thickness of the transistor, width of the source and thickness of the source. These are all different physical geometrical dimensions of a MOS transistor or PMOS transistor. There are 6 or 7 physical dimensions that are relevant to transistor physical properties. Among these, most important physical dimension is the length of the channel technology size. In the earlier versions of transistors, length of the channel were the longest dimension. Width, thickness and all other dimensions were much smaller than the length of the channel. So that's why earlier versions of MOSFET transistors were known as long channel MOSFET. So all the behavior we are going to discuss right now, assuming that the MOSFET we are using is for long channel. Because if for short channel device, when channel thickness and width and other dimensions become comparable to or equal to the channel, then we call it short channel device. Short channel device behaves slightly differently from the ideal behavior we are predicting. So don't worry about it, just it's an approximation of channel length compared to its other dimension. So now, when you want to turn on a MOSFET transistor, that means you want to, that dark shaded area indicates that the transistor is on, a channel, a layer of n-type material or n-type particle is formed between n-type source and n-type drain. So the channel is established, transistor is on. But how do we get to that stage? First, at the gate of the terminal, you have to apply a positive voltage. That positive voltage doesn't go from 0 to VDD instantaneously. You have to gradually raise it from 0 and above. The moment it goes slightly above 0, when gate terminal gets some positive, right? So under the gate, what do you have? Under the gate and the surface that channel area, it's a p-type body. P-type body means what? Heavy concentration of positive particles. So the moment gate layer becomes slightly positive, first reaction is positive gate layer will repel positive holes. So that region below the surface of the gate will be depleted from positive hole. It will become neutral first, because that is a p-type body, so it has a heavy concentration of hole. So as we make gate voltage positive, positive gate voltage will repel positive hole in the surface area, so they will be pushed downward. So that shaded area will become free from hole, because holes will be pushed back, repelled by the positive gate charge. So that first stage of operation is called depletion. So depletion is the process of depleting all the hole, pushing all the hole downward from the channel region so that it becomes free of positive holes. Because to make it n-type, we have to completely change the polarity from p-type to n-type. First we have to neutralize it by pushing down the hole. So the depletion will take place up to certain gate voltage. When the whole channel area becomes free or depleted from holes, any extra positive voltage you apply at the gate further increase, then that positive voltage will now have no hole to push back. It will start attracting electron, because positive gate voltage will attract electron. Where it will get the electron? It will get the electron from source drain, and although it's a p-type body, it has minority carriers electron. So all those electrons will be attracted upward, and they will accumulate under the surface to form the channel. So the gate voltage at the end of depletion, when electron gathering starts, that voltage is called threshold voltage. So it's for an NMOS transistor, it's a positive gate voltage when depletion will continue, but it will end and gathering of electron will start in the surface area. So that transition of characteristics, material characteristics of the channel region will take place at a voltage at the gate known as threshold voltage. So to turn on an NMOS transistor, you have to apply a gate voltage larger than the threshold voltage, because up to threshold voltage everything will be spent to create the depletion layer, and above threshold voltage any extra positive voltage will gather electron. Now if you keep increasing the gate voltage above threshold voltage, at one point that channel region will accumulate enough electron to form a continuous channel layer from source to the drain. So you started with a P-type body, then you neutralized it, depleted it, then you converted it to complete N-type region, and that phenomena is called inversion. So turning on a transistor, NMOS transistor, by applying a positive gate voltage happens in 3 steps. First, you raise the voltage, start raising the voltage above 0, depletion will take place. At one point, that whole region will become depleted. You reach the threshold voltage of the gate. Anything above threshold voltage will start accumulating electron, and if you reach much above the threshold voltage, you will have enough electron to form the channel, and that phenomena is called inversion. Further higher you go above the threshold voltage, more electron will be accumulated, your channel will become stronger and stronger. What is the highest you can go? Supply. Makes VDD. So the highest gate potential that you can apply is VDD. Now I want to introduce a very important term for MOSFET transistor, VDD minus VD, or we can say VGS, gate source voltage minus VT. Highest it can be VDD. But at any point, whatever positive voltage you apply at the gate terminal with respect to source, this voltage VGS minus VT, it's called gate drive. It's called transistor gate drive. Why it is called gate drive? Because this is the magnitude or amount of voltage that will be actually utilized to form the channel, right? Because up to threshold, you are not accumulating an electron. Above threshold, anything you accumulate up until the maximum possible voltage at the ground gate terminal is called gate drive, because that extra voltage is your voltage that is available to form the channel. So VGS minus VT, this is an important parameter, and VGS can maximum go to up to VDD. And whenever we turn on a transistor, we want to turn it on as strong as possible. So it is a standard practice that whenever we turn on a voltage, we apply up to the maximum supply voltage at the gate terminal to form the strongest possible channel between source and the drain, and that will turn it on strongly. So at the beginning, when there, as of now, we did not apply anything between source and the drain. We just applied a positive voltage large enough to form a continuous channel from source to drain. At the beginning, let's say this is the gate plate, this is my source region, this is my drain region. So I'm applying the voltage here. So from source to drain, the entire electrical field is uniformly applied to the entire body, source, drain, and the channel region. So the accumulation of charge in the channel region will be uniform from source end to the drain end. It will be uniform constant density channel area with identical electron density from source to the drain, so you will have a uniform channel. But once channel is formed, now I turn it on. But I turn it on for what? To send current from source to drain. So to send current from the source to drain, so for NMOS transistor, charge carrier is electron. The electron will enter through the source, that's why it is called source terminal. Electron will leave the transistor through the drain, that's why it is called drain terminal. Now, to form a current, you have to make sure that electrons are leaving through the drain, entering through the source terminal. To make that, I have to connect drain terminal with the positive terminal of the battery to force the electron out, and to supply or inject electron back, I have to connect source with the negative terminal. So if I connect source with the negative terminal, drain with the positive terminal, when channel is formed, what happened? Now, this side is positively attracting all the negative electrons. So electrons are pulled out of the drain, and the drain is refilling it by pulling it out of the channel. Channel will refill it by putting out from the source, but it will refill it from getting it from the source terminal from the battery. So right, there is a pull in this direction to the drain. So now this is a high concentration of electron, this is a high concentration of electron, but this is a temporary inversion layer created on top of a P. So it will not be as strong concentration as source in the drain. So the rate it will be pulling out, the rate it will be pushing in, the flow here will not be at the same rate. So as you are pulling it out, even if you take something out this way, like material, it will create a cone shape. So further increase of the drain voltage will pull electron at a much faster rate out of the channel. So the channel will no longer remain uniform. It will become a cone shape or tapered shape with a much reduced width or thickness on the drain end, because electron is getting out of the device through the drain end of the channel. So it will become like this. So yes?
The concentration of electron at the drain will reduce compared to source?
Yeah. So now you are absolutely right. So as the drain voltage gets higher and higher, more and more electron will leave, and source end will remain almost same thickness, but drain end will become narrower and narrower. That means this side will have the highest concentration of electron, this side will have the lowest concentration of electron. As we increase drain source voltage. So now let's move to the next slide. So at one point, now the question is, as you continuously increase the drain voltage, more and more electron will leave the tip of the channel at a rate much faster than it can be refilled by the source. So if the rate of electron leaving the channel is higher than rate of electron coming back to the source, then what will happen? Temporarily, there will be a gap created at the top tip of the channel, as if you are cutting the channel shorter. That condition is called pinch off. That condition is called pinch off condition. You are pulling electron out of the channel at a much faster rate than through the drain terminal, then the source can refill it back to the channel. So on the top of the channel where electron is leaving the channel, there temporarily a gap will be created, and that phenomena is called pinch off region. So, but we will talk about the voltage limit, but let's explain the operation before the pinch off. Initially, by applying a gate voltage equal to supply, we formed a strong channel. Now, to flow the current through the transistor, we connect battery between source and the drain. Current will start flowing. As we are increasing the drain voltage, current will increase. So current will increase initially linearly as we increase the drain voltage. So drain voltage is VDS. Current through the transistor is denoted as ID because the current is coming out of the drain terminal, that's why it's called ID. ID initially will remain linearly proportional to VDS because as we increase drain voltage, the current will move faster because you are increasing the battery voltage. So the ID current will linearly increase initially with VDS. But gradually, as you reach towards pinch off, a portion of the channel disappears. A portion of the channel disappears. So at the tip of the channel there is a gap. So there is no easy path, channel for the electron to flow from the tip of the channel to the drain terminal. So because there is a physical electrical gap. So any extra voltage you apply to the drain terminal will be needed to tunnel, to pull against the will of the electron from the tip of the channel through this gap to the drain. That's why current, all the excess voltage, all the excess energy will be spent to drag the electron through the gap region from channel to the drain. So the current will no longer increase. So at pinch of point, when it will reach the pinch of point, current will gradually become saturated. At one point, further increase of drain voltage will no longer give us current increase. So this is called linear region of operation. This is called saturation region of operation. We'll explain it later again, so don't worry. So in the linear region, current will linearly increase, or almost linearly increase with the drain current, drain voltage. In the saturation region, current will become independent or insensitive to further increase of drain voltage, and the transition happens at the pinch of point. Now the question is, let's explain why pinch off happens and when it happens. So when the transistor is on and working means there is a current flowing through the source and the drain terminal. It is delivering current to something else. So it is working. When the transistor is in operation, there are two voltages that are applied across the channel. First voltage is the vertically across the channel, the gate source voltage to form the channel. Second voltage is horizontally along the length of the channel, that is source to drain voltage to flow the current. So at any given time, the channel electrons are experiencing two electrical field or two voltages, one vertically due to the gate voltage, one horizontally due to the drain voltage. So an electron to remain in the channel region, the resultant electrical field, that means electrical field due to the drain voltage minus the electrical field due to the gate drive must be positive for it to basically get out of the channel. Or if it is negative, if that vertical one is stronger, the channel electron will remain in its place. Since drain voltage is applied from here, drain voltage will be stronger here, field, but gate field is uniform all over. So this drain voltage minus the gate voltage field will become positive at the drain end of the channel first, so those electrons will leave. And that's why the pinch off will start happening at the drain end, not at the source end. So now let us basically explain in general term. At any given point, what is the total resultant electrical field acting on any electron along the channel? VGS, gate voltage, minus V of Y, which is drain voltage along the channel. why instead of writing VDS, I wrote V of Y. When I apply the drain voltage is applied across source to drain. That means the ground terminal of the drain voltage is connected to the source, positive terminal of the drain voltage is connected to the drain terminal. If the channel length is Y, along the direction of Y, VDS is 0 at source end, VDS is highest equal to VDS at the drain end, right? But at any given point Y along the channel, the total resulting voltage on an electron will be VGS minus VY minus VT, by the way, because for gate voltage, anything up to VT is not useful to form the channel. Above threshold voltage, so I should actually write it in a different way. The resultant electrical field on any electrode will be gate drive minus V of Y, right? V of Y is the effective drain voltage at any given point Y along the channel of the transistor. So, because I am assuming, because this is source end, this is drain end, this is 0 voltage, this is VDS. If this direction is Y, if the length is Y, variable along the length at any point, this is the effective drain voltage, right? Because it is 0 at the source end, it is maximum VDD or VDS at the drain end. At any general point Vy, it will be, to the general point Y, it will be V of Y. Now, pinch off occurs when this becomes equal to 0. Gate drive, when it becomes equal to the drain voltage, that means there is nothing there to keep that electron attracted in the channel. Effective electrical field for the channel to remain, for the electron to remain in the channel becomes 0 at this point, right? So, when this, which point will satisfy this condition? The tip of the channel at the drain end, when drain voltage become equal to saturation voltage, that's when this condition will happen. So now the question is that what is the drain saturation voltage VD set we are talking about? With the increase of drain voltage, channel will become tapered and narrower on the drain end. At one point, the channel will disappear from the drain end. That condition is called pinch off. Beyond pinch off, further increase of drain voltage will not increase the drain current. That means it entered into the saturation. So that saturation linear will end at the pinch off point, saturation will start. So the corresponding drain voltage at pinch off is called VD set. Drain saturation voltage. When drain voltage reaches this voltage, further increase of drain current will not happen. So at the drain end of the source, this will satisfy first, because then this will become equal to 0. When there is 0 effective voltage on any electron along the channel, that electron will not have any force to be attached to that layer to be in the channel. So this condition will satisfy when gate drive VGS minus VT minus VD set becomes equal to 0, right? So how do we calculate when drain enters saturation? VD set is nothing but equal to gate drive. So it's the logical. When drain voltage and the gate drive becomes equal, resultant electrical field is 0. So there is no force for the electron to remain in the channel area. So drain saturation voltage, when pinch off will start happening, when the transistor enters into saturation, will be equal to gate drive. So for the drain voltage when it becomes equal to saturation voltage, which is equal to gate drive, pinch off condition will happen. Yes.
What's VT? Your VT
Threshold.
threshold.
VTS
Okay, VT.
set. Yeah.
VT. It's threshold, right?
Yeah, VT is the threshold voltage, because for the gate voltage we have to always subtract threshold voltage to calculate the gate drive.
Yeah.
Because up to threshold voltage no channel is formed, and this is drain saturation voltage. So now if we basically want to again go through the operational steps of the NMOS transistor. First, application of any gate voltage above 0 will force depletion, and up to threshold voltage depletion will continue. Above threshold voltage, channel will start forming. At one point, for a reasonably high gate voltage, and a strong channel will be formed, and that phenomena is called inversion, because we are converting a p-type body area to an n-type channel. So it's called inversion. And then when inversion takes place, channel is formed, the transistor is on, and then we apply the source drain voltage with respect to the source. Current will start flowing through the drain, and the channel will become narrower and narrower at the drain end. When drain voltage reaches its saturation voltage, a pinch off phenomena will take place. That means top of the channel will become pinched off, will become kind of depleted. So the channel will be like as if it's hanging there. So any extra drain voltage you apply above saturation will be needed to physically drag the electron to this pinched off region from the channel to the source, which will not contribute to the current conduction. Yes?
VDS is constant the entire time.
No, VDS is constantly increasing,
Okay.
and finally the maximum VDS we are going to apply is VDD. So same thing for VGS and VDD, ultimate destination is VDD. So, but in actual transistor operation, VGS will always apply VDD, no matter what, because we want a strong channel. But VDS, maximum you can go up to VDD supply, but depending on your application, sometimes you want to operate your transistor in the linear region, so you keep your VDS below saturation. Sometimes you want to operate your transistor in the saturation region. Majority of the logic and memory application, it is operated in the saturation region. So you apply a voltage equal to VDD above saturation voltage. But for some sensing application, for some analog application, MOSFETs are used and they are operated in the linear region where you apply a VDS smaller than saturation voltage. So before we further explain the MOSFET operation, this is a very, very important slide. You need to understand MOSFET's structural electrical characteristics and formation of capacitors. And actually, this will be the most important parameter, the capacitance, structural capacitance within the MOSFET device. This will be the most important parameters that will determine speed, power consumption, and other performance parameter of MOSFET transistor. And it is related to everything else we have discussed so far. So, just for the time being, forget the fact that it's a MOSFET device or transistor we're talking about. Just look at this structure purely from material point of view. We have 4 layers of material, a gate layer, an N-type source, N-type drain, and P-type body. They are placed in a certain geometric pattern with respect to each other. The gate is a conducting layer separated from the channel area by an electrical insulator. The channel area is not a conductor, but it's a semiconductor. It has some conductivity. So, an electrical conductor separated from another electrical plate by an insulation, what do you get? A basic capacitor. A two electrical plate separated by an insulator, you get what? Capacitor. And that is called gate channel capacitance of MOSFET transistor, the most important defining characteristics of MOSFET device. Everything else we have discussed will depend on, and everything else we are going to discuss in terms of speed and power consumption, energy efficiency, will be dependent on the value of this gate capacitance. So now we know that capacitance definition, when an electrical plate separated from another electrical plate by an insulator, a capacitance is formed. The value of that capacitance is epsilon, electrical permittivity, what? Thickness D by W, right? The area of the plate and the distance of T or D or T, whatever distance, if the area is A, right? Capacitance is epsilon, it's actually is W by L. Its capacitance C is epsilon A over T or D. That is the basic definition of capacitance, electrical circuit 101. Now, across the gate channel, that capacitance is formed because of the presence of the silicon dioxide, and it is separating a conducting gate layer from a semiconducting body channel area. So a channel capacitance will be formed. So what will be the value of the channel capacitance? Epsilon. What epsilon are talking about? Electrical permittivity of the silicon dioxide, epsilon oxide, right? The area that is overlapping between gate and the channel is what? The area of the bottom surface, right? Which is width of the gate or the channel times W. That is the area of the bottom surface overlapping with the channel. So the area A is W times L, which is thick width of the device times length of the device, divided by this thickness D. What it is? It is the distance between gate plate and the channel, which is nothing but thickness of the silicon dioxide, right? Thickness of the silicon dioxide is the distance between gate plate and the channel. So the gate channel capacitance is epsilon oxide, permittivity of silicon dioxide, area, bottom area of the gate plate or the top area of the channel region, W times L, divided by T oxide. So typically, we know that silicon dioxide has a constant permittivity. Typically, for a certain technology generation, we do not change silicon dioxide thickness from transistor to transistor. For an 18 nanometer transistor technology, every transistor will use, let's say, 2 nanometer silicon dioxide thickness. It is fixed for that technology. So if for a certain technology, epsilon oxide is a material property of silicon dioxide, if the thickness of the silicon dioxide is fixed, so this is a constant for a certain technology generation. So, and we can also say that if the and then the length is what? Length is related to technology generation. Typically, when you are going to design an IC, if they say you have to design it with 18 nanometer, automatically your transistor length is fixed. You cannot change as a designer length of the transistor or the technology size. But if you need wider and narrower transistor, only dimension you can play with is W, the width of the transistor. You as the VLSI designer, you do not have control of the thickness of silicon dioxide, you do not have control on the length or technology size of the transistor. It is divided by device engineer. You can only play with the width of the transistor to get wider transistor or narrower transistor. So now that the length L also is constant. So this whole thing, epsilon XL, is called per micron capacitance for a particular technology. as if W equal to 1, this is the capacitance, right? So that's called it is per micron. So now for a technology generation, for let's say 80 nanometer technology, they will tell you that for this technology generation, per micron gate capacitance is this. It is coming from epsilon divided by T times L, assuming that W equal to 1. So if you know what width you are selecting, let's say 10 micrometer width you are selecting, so the total gate channel capacitance will be this times W, the thickness, right? So the width of, so that is basically, but the question is why you need to calculate this gate capacitance. Why this, as I am repeatedly saying, this is one of the most important device parameters that determines performance and functionality of MOSFET transistor. We will explain it in a bit. But now, from the basic definition of capacitance and relating it to this gate channel capacitance, what we can see from this top equation. In any given design, if you want to increase the gate channel capacitance, you can play with the width, you can increase the width, capacitance will increase. You can increase the length if they give you freedom, it will increase the capacitance. Or you can reduce the thickness of silicon dioxide because it is in the denominator, it will increase the capacitance, right? Or you can move to another material because epsilon is a constant material property for silicon dioxide. If you can move to a different material with higher epsilon, you get higher gate channel capacitance. If you move to a material with lower epsilon, you get lower gate channel capacitance per unit area. So, from this relation, I am trying to establish what design parameters you can play with as a designer if you want to get higher gate channel capacitance or lower gate channel capacitance. 3 geometric parameters: width of the transistor, length of the transistor, thickness of the oxide layer. You can play with these geometric parameters and one material property, epsilon. So all the new device level research for next generation, basically semiconductor device, all the research are going around those 3 physical dimensions or 1 material dimension to improve the device characteristics. Now we are going to talk about why this transistor capacitance is so important. When I am applying, let's say it's an NMOS transistor, when I am applying a gate voltage, positive gate voltage, gate becoming positively ionized. And this is a capacitor, right? Capacitor's property is when you apply a positive voltage here, it induces a negative voltage on the other plate, right? By accumulating electron. That is what is happening in the channel formation. But the magnitude or the strength of capacitance will determine how strong this negative layer is. If you have larger capacitance across the gate channel, you have stronger negative layer, ionized, accumulated on the channel side. So ultimately, the strength of your channel or conductivity of your transistor is dependent on the magnitude of the capacitance you are achieving across the gate channel area. Larger the capacitance, your channel will be stronger. That means higher magnitude of negative charge will accumulate on the channel side. Because, so now, ability of a capacitor to accumulate charge, ability of a capacitor to accumulate charge, Q is equal to what? CV, another basic electrical formula. Now, if the capacitance value is higher, for the same small voltage, you can accumulate more charge. Your channel will be stronger. If the capacitance remains constant, to make your channel stronger, you have to accumulate more charge, you have to increase the voltage. But to operate any IC at a much higher energy efficiency, what do you have to do? You have to be able to push more current with less voltage. That is called energy efficiency. If I can do more work, get more current out of smaller voltage, that means my circuit is more efficient, higher speed, more energy efficient. That means instead of raising the voltage to get more current, which will consume more power, what if I don't increase the voltage? If I can increase the capacitance, so the value of the capacitance will determine how much charge you can accumulate into the channel, how stronger the channel will be. Stronger the channel means more electron accumulated, and the current conduction capacity of the transistor will be higher for a smaller voltage. Yes.
So you're talking about increasing capacitance. So in different material, the capacitance will be different.
Yes.
Then we can increase by using different materials.
Yes. So that's basically the device engineers are doing. They're exploring like 10 different insulators for the same thickness. Can we get higher epsilon so that for the same dimension you get significantly more capacitance. So even for a smaller voltage, you can now create a stronger channel. Yes.
Well, wouldn't increasing the capacitance also increase the time constant? Because
Very important observation. So it's
Yes.
a trade-off. So there are some capacitance in the device we want to increase, not all of them. So it's a trade-off between energy efficiency and speed. Because increasing, very good observation, increasing capacitance will increase RC time constant and it will increase the delay.
Delay.
Yeah, but that's why it's a trade-off. That's why unilaterally we cannot increase the capacitance. We have to reduce the voltage and many other factors basically to get the desired speed and energy efficiency. That's why in IC design there is nothing called best design. It is always optimum design. Compromise between speed and energy efficiency. Yes.
You have told like if we decrease the voltage, increase the current, that's efficiency.
Yeah.
But if we increase the current, the heat, there will be much more heat produces.
So the question is that from the same amount of voltage you can get more current. That means you can do more work. Let's say you are operating a logic circuit with 100 logic gate. Each logic gate will need certain amount of signal to be turned on and off. If for the smaller amount of voltage you can get more current, that means using the same current now, you can turn off 110. From the same voltage you can turn on 110 logic gate because you are getting more current. But individually, if you can operate each of those individual logic gate at a much lower voltage, then your energy efficiency will increase. But again, there is a trade-off, as I said, because you cannot just increase or decrease one parameter unilaterally. So now it is important because in the subsequent discussion we will talk about gate capacitance. But now, based on what we have discussed so far, let us divide the operation of a MOSFET transistor or NMOS or PMOS transistor from the beginning to end. So at the beginning, what we have seen, at the gate terminal, the gate voltage is called VGS. We started from 0 and we increased it up to VT, positive voltage, is a positive voltage. But from 0 to VT, threshold voltage at the gate terminal, the channel is not yet formed. just depletion is taking place. Still, source and the drain is disconnected because no channel is formed. During that state of transistor operation, we are calling it cutoff state of transistor operation. From gate voltage equal to 0 up until threshold voltage, no channel is formed, no connection from source to drain, it is called cutoff. And then when VGS equal to VT, then above that channel is formed, and then when VDS drain voltage is starting from 0 towards VDD, at one point it will be at VD set. Initially this is above threshold voltage, a channel is formed. Initially current ID will linearly increase with the increase of VDS. That gives us second state of transistor operation, linear state or linear region of operation. For the linear region of operation to take place, gate voltage must be greater than threshold voltage for the channel to be formed, and the drain voltage should be any voltage between 0 to saturation voltage. That is for linear. But for gate voltage above threshold voltage, but drain voltage at or above saturation, current will no longer increase, it will become saturated. So that gives us the third region or state of transistor operation, saturation. Saturation region or saturation state. For this to take place, gate voltage has to be greater than threshold voltage, drain voltage has to be equal to or greater than drain saturation voltage, which is gate drive minus VT. So this is what I have summarized here, that there will be three regions of operation when the transistor is working. First is the cutoff or the subthreshold region of operation. It is called subthreshold because it is for the range of gate voltage below threshold voltage. So subthreshold region of operation. Linear or non-saturation region when the gate voltage is above threshold voltage but drain voltage is below saturation voltage, then current will be linearly proportional to drain voltage. It is called linear region of operation. Also it is known as resistive mode of operation because it is working like a resistance. Across a resistor, if you increase the voltage, current will linearly increase. But when the drain voltage reaches the saturation voltage, current will no longer increase with drain voltage, and that is called saturation region of operation for the MOSFET transistor. So this will take some time because this slide it is actually deriving the current equation. So I will go in the next class step by step. But up until now, any confusion for any of these slides up to 27?
I have one question, like
Yes.
why it's pinched off, like the. Can you explain it one more time?
Oh.
The pinched off.
Pinched off condition. Good question because you have to be very clear. So, when channel is formed without the application of the drain voltage, it's at a uniform channel.
Yeah.
And then when channel is formed, now you apply a voltage between drain and source. And that voltage will have positive terminal connected to the drain, ground terminal or the negative terminal connected to the source. Now from 0 you are continuously increasing, so the electron will be pulled out of the drain. Electron will be pulled. So if you have, let's say, lots of marble here, they're all, now if you apply a force from here to attract those marble, free flowing marble, they will create a cone shape because you are pulling it from here. Now, if there is something refilling it at the same rate, then the channel will remain intact. Marble, there will be always a layer of marble here. But if, as I am increasing this attraction force, the drain voltage, higher and higher, these marbles are falling out of this table at a much faster rate, then it can be refilled from here. That's why I have created a channel here. So that's why I am taking it out at a much faster rate than I am pushing it back. That's why temporarily at higher drain voltage there will be a gap created, as if the channel is hanging on the one end, on the drain end. That disappearance of channel from the drain end, temporary disappearance of channel at high drain voltage is called pinch-off condition.
So that means we also need to have a threshold for the drain to get
So-
the drain, to stop the drain for extracting too much of electron.
No, that basically the start, the beginning of the pinch-off is called saturation.
Yeah.
Now-
oh yeah.
So
Oh, I forgot.
saturation, you can increase the drain voltage up to VDD. So this additional voltage you are applying above saturation voltage, where it is going, it is not increasing the current because current becomes saturated. So because now originally I had a constant channel, now I had a tapered channel which did not reach the drain end. So now the channel disappeared from this side. So now this is a p-type layer. This is an n-type truncated channel.
Yeah.
So now electron will freely flow from the tip of the channel. Now from the tip of the channel to the drain, current to continue, you have to basically pull the electron with a strong force, like as if physically dragging it from the tip of the channel to the drain. So this extra energy, voltage, from saturation to VDD will be spent to drag the electron here. At the tip of the channel, the voltage will become constant at VD set. Anything above will be needed to physically drag the electron through this depleted pinch-off area. That's why current will become constant.
That's a huge amount of energy, right?
Yes.
So when the channel's uniform, it's just you have a short basically.
Yeah, it's acting like a, it will have a finite resistance.
Right.
It is acting like a resistor. That's why it is called linear or resistive region of operation. When channel is, a continuous channel is there.
Like
Yes.
it is in a standby mode, like they are standing still, the electrons are not moving, right?
Electrons will stay in the region as long as there is a positive pull towards the gate. Yes.
So we were talking about how capacitance makes this channel stronger. Can you
Yeah.
ever have enough capacitance to get rid of that pinch-off condition?
No, so basically the question is for the capacitance, very important question and very good observation. The question is that across the gate, I am forming a capacitance. This is positive, this is negative. Now, just think about from capacitance, for this portion of the capacitance to remain negatively ionized, there has to be an effective positive voltage active here. But in this point, that capacitance is disappearing. Why? Because this VGS minus VT, the gate drive, the voltage that I am applying from here to here on this capacitive plate, minus this Vy, it becomes equal to 0. So effectively from this side, this end of the capacitance is not having an effective voltage applied across them. So the capacitance will become effectively 0. So the accumulated charge Q will be Q times V, so it will be 0 times V. So that's why. For a capacitance to remain effective, you have to have a voltage difference. So if a physical capacitance C, if the effective voltage V is 0, no matter how strong the capacitance is, accumulated charge Q will be capacitance times 0 voltage equal to 0. So, stronger capacitance will help you form the channel faster at a lower voltage. So the device threshold voltage will go down. So one of the benefit of having a stronger voltage is because of the stronger capacitance, benefit is for a stronger capacitance, this negative channel will be formed with much lower voltage. That means this threshold voltage, this is up to the threshold voltage, we don't form any channel. That threshold voltage magnitude will come down. That means my gate drive available voltage to form the channel will increase with stronger capacitance. So, now, in the entire course, in the entire VLSI design, lecture 2 is the most important lecture. If you go for any interview with Intel or AMD or any company, if you understand lecture 2 and 3 very well, you can answer any question. If you do not understand these two lectures, particularly lecture 2, operation and the design of MOSFET, and lecture 3 or 4, the basics of CMOS circuit design, then everything else. So many students tell me that all the questions came from lecture 2 and 3. So, because it gives you the basics of any digital, micro and nano electronic design. So I request that you spend a lot of time on lecture 2 material. Ask me questions 100 times. Stop by, from next week I will be declaring office hours. Stop by during the office hour, because if your concept and understanding is 100% clear in lecture 2, you will struggle for rest of the class, even for future courses. Okay. That's all.